Today we'll be discussing problems involving weak bases. We know when acids are placed in water, it gets disassociated by the water to produce its conjugate base and the protonated water, which we normally just term as H+. But with weak bases, it reacts with water, so it's associating into its protonated form and the deprotonated water, called a hydroxyl. So the equation for that association can be written like this, where the NH3 is the BOH, the denominator. The NH4+ is the B+, known as a conjugate acid, and the hydroxyl. In problems, it might state that you're starting with a base buffer, which means that before putting in water, we have a weak base, like NH3, that gets partially associated in water. So we have a mixture of our weak base and the conjugate acid. So let's look at how we might use Kb for problems. We know that for weak acids, we use the normal HH equation, but there's a base version of the equation too, which we can solve for the POH. Here's a list of the common weak bases you might see in problems. Notice most of them contain an amine and/or end with a hydroxyl group. A chemical that deviates from this pattern is nitric and nitrous acid. They are acids, not bases, even though they contain a nitrogen, so just watch out for them. As a recap, the Kb equation is written like this, where the denominator is our base, and the numerator consists of our conjugate acid and our deprotonated water, called a hydroxyl. To determine the moles of NH4Cl that must be added to 0.15 liters of 0.2 molars NH3 to produce a buffer with pH of 7.5, and we're given the Kb. Our NH4Cl gets disassociated into NH4, that will serve as our conjugate acid, or BH, and the NH3 will serve as our base. We also have a Kb, which means we can use our modified HH equation for bases. So we'll first convert pH to POH. To get that, it's just 14 minus the pH, which gets us 6.5. Now we'll convert Kb to pKb. To do that, we'll take the negative log of the Kb, which gets us 4.74. Now, to find the moles of our base, we'll multiply the molars with the liters, like so, and solve for the conjugate acid, the BH. First, we'll move the 4.74 over, then we'll do base 10 on both sides to cancel out log, multiply both sides by 0.03, and get us our answer. So a 30 milliliter sample of 0.5 molar CH3NH2 is being titrated with 1.5 molar HCl. What is the pH of the solution after 5 milliliters of the acid has been added? And the Kb is given to us. Since we know HCl is a strong acid, that means CH3NH2 is our weak base. And since we have the molars and liters of our base, we multiply them with each other to get us our moles. The same can be done for the HCl. So now that we have the moles of our molecules, we can put it into our ice table. So we know that we're starting with a weak base in water, and bases like to take hydrogens, in which it will take one from H2O to form our conjugate acid, our BH, and whatever is left of our water. We are adding HCl, which is a strong acid, which means it will react with our base, which is on the left side of the equation. Now that we have our equation, we can put in the moles we calculated from before. The strong acid will completely react with the weak acid, so both will go down by 0.0075 moles. And whatever we subtract on one side, we add on the other. These are the ending moles of our weak base, the conjugate acid, the BH, and our OH, which we won't use, so we can ignore it for now. Now we can plug these values into our modified HH equation, like so. And since we have the Kb to convert it to pKb, we'll just take the negative log of it, which gets us 3.19, and now we can just solve for the POH, which gets us this. And to get to pH, we'll subtract 14 from our answer and get us our pH. So there's an alternative method for solving pH involving weak bases, so it's up to you and which you prefer. Rather than memorizing this modified HH equation on the bottom, we can just convert the Kb from the problem to a Ka using this equation, where Kw is always 1 times 10 to the negative 14. So let's do a problem. For a buffer containing CH3NH2 and CH3NH3Cl, calculate the base to acid ratio to make its pH that of 10.5, and the Kb is given to us. So since we're given the Kb, it means that we're dealing with a weak base, and we know the difference between these two buffer molecules is that one has one more hydrogen than the other. The one with the less hydrogen is our base, and the one with the extra hydrogen is our acid. From here, we'll use the normal HH equation, and right off the bat, we know our pH is 10.5. But we also need to convert this Kb to a pKa. First, we'll convert the Kb to a Ka, where Kw is always 1 times 10 to the negative 14. We'll plug in our Kb to solve for Ka, like so. Now to go from Ka to pKa, we'll just take the negative log of the Ka, and we'll plug that value into our equation. Since the question is asking us to find the base to acid ratio, we don't need to individually find the A- and HA. In other words, we're all set. We'll move the 10.64 over, take the base 10 of both sides to cancel out log. So let's make this answer resemble the fraction on the right by putting the whole thing over 1. So it tells us for every one of our HA, 0.72 of our A- is needed to get to the pH of 10.5. To make it really accurate, as we said before, the one with the lesser hydrogens is our base, the A-, and the one with the more hydrogens is our acid, the HA. Next, we'll deal with questions involving this term called equivalence point. So equivalence point is where the moles of buffer we have originally is equal to the moles we have of our strong acid / base. And if that sounds confusing, just know that at the equivalence point, everything on one side of the arrow in the ice table will go down to 0. Like so. So let's do a problem. 35 milliliters of 0.15 molar NaOH is used to titrate 200 milliliters of HNO3 to the equivalence point. Determine the concentration of HNO3. First, we'll set up our equation, and we do our ice table and fill in our values with moles. For NaOH, we'll multiply the molars by the volume to get us our moles. But for HNO3, we only have the volume. What we do know is that it's multiplied by some molar concentration to get us our moles of HNO3. Since we're going to the equivalence point, remember, that just means everything on one side of the equation will go down to 0. So we know the ending moles of HNO3 has to be the same as the NaOH. To find this molarity, also known as the concentration, we'll set up our equation like this, which gets us our answer. Usually in buffer solutions, the strong acid and base is in smaller amounts than the buffer mixture itself. So what if it's higher? What do we do then? So let's do a problem to answer that. Determine the pH of a mixture of 0.15 molar NaHCO3 and 0.3 molar HCl in a liter of solution. So our HCO3 here is our weak base buffer, and the HCl is our strong acid. First, we'll set up our equation. We know our molar and volumes, which multiplied together get us our moles, so we'll plug that into our ice table. And we know all of the HCl will react with this weak base, but in this case, it's more than the amount of HCO3 we have. It's more than the amount of HCO3 we have. So we still have some of the HCl left over. And we know with strong acids, when placed in water, nearly 100% will be disassociated. Therefore, the H+ concentration will be equal to the molars of that strong acid that we have left over. So we'll set up our equation for finding pH of a strong acid like this, which gets us our answer. So very rare in problems, there are times when a solution is placed in water where you need to take account of the water itself. This is the rare moment when the concentration is very low, and by that, where the exponent is -6 or lower. For these problems, keep in mind that water has the following H+ and OH- concentrations. And it's always like this in problems, but we never deal with it just because it's such a low value. So let's go through a problem. Determine the pH of a 5 × 10⁻⁴ millimolar solution of KOH in water. So we know we're starting off with a strong base, and so we'll be looking at water's hydroxyl concentration. First, we'll convert our millimolars to molars, which gets us this. And because this value is so small, again, an exponent of -6 and lower is a good cutoff point, we add the amount of OH minus from KOH to the amount of OH minus from water. And so our total OH minus value is the following. And to get the POH, we'll just take the negative log of it and subtract by 14 to get us our answer in pH.